So, have you ever stopped and wondered, how do we make sense of everything? I mean, the universe is packed with stuff. The air you're breathing, the phone in your hand, it's all made from these basic ingredients called elements. But here's the catch. There are over 100 of them. How in the world do you even start to organize all that? Well, that single question led to one of the most brilliant inventions in all of science. Today, we're going to crack the code of the ultimate chemistry cheat sheet, the periodic table.
Okay, to get what I mean, just picture this. Imagine you're in charge of a massive shipping port. You've got thousands upon thousands of containers coming in every single day. They're all different sizes, different weights, going to different places. Without a system, it's just pure chaos, right? You absolutely need some kind of logical grid, a master plan, so you know where everything is and where it's supposed to go.
All right, section 1, organizing the elements. And believe me, for the chemists back in the day, this was a huge problem. It was basically the #1 mystery they were trying to solve.
So, those chemists, they were facing that exact same container port problem. How do you sort the fundamental building blocks of the entire universe? They'd found all these elements, and each one had its own personality. You had shiny metals, you had invisible gases, some were so wild they'd literally explode if they touched water, while others were kind of lazy and wouldn't react with anything at all. They just knew there had to be a pattern hidden in all that chaos. But what was it? What was the secret key?
Okay, let's get into section 2, the table's secret code. The solution they came up with was just brilliant. It was this amazing chart that didn't just organize what they already knew, it could actually predict things about elements they hadn't even discovered yet. And the whole thing, the entire system, was built on one single, simple rule.
And here it is, the periodic table. Now, I know, at first glance, it might look a little intimidating, but the real genius of this thing is how incredibly simple the idea behind it is. Every single one of the 118 known elements has its own special spot on this grid, like its own address. And that address tells you everything you need to know about it. So, what's that secret code? It's called the periodic law, and it's this. If you line up all the elements in order of their proton number, their atomic number, something amazing happens. Their properties start repeating in predictable patterns. It's like a rhythm. But why? Well, it's because the number of protons dictates the number of electrons, and it's how those electrons are arranged that gives an element its unique personality. That's it. That one little rule, line them up by proton number, is the key that unlocks the entire thing.
Moving on to section 3, reading rows and columns. So, we've got the secret code. Now let's figure out how to actually read this map. Because all the good stuff, all the secrets, are hidden right there in the rows and columns. The geography of the table is actually super simple. The rows that go across, we call those periods. The columns that go up and down, those are called groups. And an element's address, its period, and its group number isn't just a random spot. Oh no, it's a code that tells you exactly how that element is built and, more importantly, how it's going to behave. So let's decode it.
All right, let's start with the rows, the periods. Take a look at period 3. Every single element in this row, all the way from sodium on the left to argon on the right, they all share one big thing in common. Check out their electron structures. See how sodium is 281 and the next one is 282? They all have 3 numbers in their configuration, and that's because every element in period 3 has, you guessed it, 3 electron shells. The rule is just that easy. Period number tells you the number of electron shells. Simple as that.
Okay, what about the columns, the groups? Well, an element's group number comes from its valence electrons. That's just a fancy term for the electrons in its outermost shell. And these electrons are the real VIPs. They're the ones on the front line, the ones that actually get involved in chemical reactions. So for the main groups, it's a piece of cake. If you're in group 1, you've got 1 valence electron. Group 2, 2 valence electrons. Jump all the way over to group 17, and you've got 7. This number is the absolute key to figuring out an element's whole personality.
All right, pop quiz. Let's put this to the test. Imagine you're a chemist and you find a new element. You do some tests and find its electron configuration is 287. So, based on the 2 rules we just learned, can you find its address? Where does it live on the periodic table?
Go on, take a second and figure it out. So, how'd you do? Let's break it down. The configuration is 2, 8, 7. First, count the numbers. 1, 2, 3. That means 3 electron shells, so it has to be in period 3. Simple. Now look at the last number. It's 7. That means it has 7 valence electrons, so it must be in group 17. Now go find that address, period 3, group 17, and boom, it's chlorine. See? You're already reading the map. It's not so bad, is it?
All right, section 4, meet the chemical families. Now this is where it gets really cool. Since all the elements in the same group, the same column, have the same number of valence electrons, they act like a family. They have similar personalities, and they behave in similar ways. So let's meet a few of the table's most famous families.
First up, say hello to the alkali metals over in group 1. These guys are the rock stars of reactivity. They've only got that one lonely electron in their outer shell, and they are desperate to get rid of it so they can have a nice, stable, full inner shell. This makes them, well, let's just say they're extremely reactive. And there's a really clear trend in this family. As you go down the group, say from lithium to potassium, the atoms get bigger and bigger. That single valence electron is now way farther away from the nucleus at the center. And there are more shells of other electrons in between, kind of shielding it. All this makes that outer electron way easier to lose. And that's why their reactivity just skyrockets. It's the difference between lithium, which just kind of fizzes in water, and potassium, which goes off like a firecracker.
Now, let's jump all the way across the table to group 17. Meet the halogens. These elements are the total opposite of the alkali metals. They have 7 valence electrons, so they are just 1 electron away from having a perfect, full outer shell. They are desperate to gain an electron, which also makes them super reactive. But here's the twist. Their trend is the other way around. As you go down their group, the atoms get bigger, and it actually gets harder for the nucleus to pull in that extra electron it wants, so they become less reactive as you go down. And last but not least, over in group 18, we find the noble gases. You can think of these as the cool kids of the periodic table. They've already got what every other element wants, a completely full outer shell. They don't need to gain electrons, they don't need to lose them, they're perfectly stable and happy just the way they are. This makes them chemically, well, content. They're unreactive. They just chill. So we've seen what happens when you go down a group. But what happens when you go across a period, from left to right? You see the biggest change in all of chemistry. You go from being a metal to being a nonmetal. On the left side, you have the metals. What do? They love to lose electrons. On the right side, you have the nonmetals. And what do they love to do? They love to gain electrons. It's a fundamental shift, and this visual makes it super clear. Just follow along period 3 with me. You start on the far left with sodium, a classic superreactive metal. Then you move across, you hit things like silicon in the middle, which is a metalloid, kind of has a foot in both worlds, and you end up on the right with chlorine, a classic nonmetal, and finally argon, a noble gas. It's a whole journey from metallic to nonmetallic all in one row. Okay, final section, number 5, the ultimate chemistry cheat sheet. Let's pull all these threads together, because the biggest mistake people make is thinking you have to memorize this thing. You don't. It's a tool. A powerful predictive tool. This mind map really shows the beautiful logic of it all. See how everything starts from one place? The proton number. That's your starting point. That one number tells you where an element goes. It sorts it into its period and its group. And once you have that address, you can figure out everything else. You know the number of electron shells, you know the valence electrons, you know what family it belongs to, and you can even predict how it's going to behave. It's a perfect, complete system. So, if you take away just one thing from all this, please let it be this. The periodic table is a tool for thinking, not a chart for memorizing. Seriously, it's a predictive engine. Once you get the rules, you can figure out the secrets of any element just by finding its home on this map. So, I'm going to leave you with one last puzzle to think about. Chemists have actually made element 118. It's called oganesson. And it sits right at the very bottom of group 18, the noble gases. Now, based on its address, what would you predict its properties are? You'd think it would be another unreactive noble gas, right? Just like the rest of its family. Or
Do those trends we talked about with atoms getting bigger and bigger hint that maybe, just maybe, something different is going on down there? The clues, they're all in the table. It's up to you to figure it out.